Unless you have superpowers, sound is heard with ears and light is seen with eyes. However, the senses of hearing and sight of humans can only identify a narrow range of sound and light.
In physics, sound, like light, is a kind of wave. Moreover, they are classified as different types of wave according to their frequencies or wavelength. A variety of sound and light is derived from different frequencies or wavelengths. Well then, what is a wavelength?
In essence, a wave is the disturbance of space. For example, the transmission of sound in the air is caused by the backward and forward movements of air particles in the air, while the propagation of light is due to the oscillation of a pair of electromagnetic fields that are perpendicular to each other. Regardless of whether it is the movements of air particles or the oscillation of electromagnetic fields, when a wave is moving forward, there will be particles or electromagnetic fields that have the same displacement from the equilibrium position at any particular time instant. We say that they are vibrating in phase at different positions.
Does that sound difficult? You'll understand once we look at this example.
If, at any time, two people on two swings are at their corresponding positions with the other, we say that they are moving in phase. For example, when the one on the left reaches its highest point, the one on the right would also reach its highest point. When the one on the left reaches its lowest point, the one on the right would also reach its lowest point, etc.
Same as frequency, wavelength is a term in physics. It refers to the shortest distance between 2 points in a progressive wave that have the same displacement from the equilibrium position at any particular time instant.
In transverse wave, wavelength is the distance between two neighboring points which are in phase. It is usually the distance between two neighboring troughs or crests. In longitudinal wave, wavelength is the distance between two neighboring compressions or rarefactions.
A wave with a higher frequency has a shorter wavelength, whereas a wave with a lower frequency has a longer wavelength. Why is there such a relationship?
We can think about this question in this way. Firstly, in physics, frequency is the number of vibrations of a wave in 1 second. This means the number of waves that passes through a certain point per second. So the distance traveled by a wave in 1 second is equal to the frequency multiplied by the wavelength. That is the velocity of the wave.
Be they sound wave or light wave, the velocity of a wave in a particular medium is constant. So the higher the frequency of a wave, the shorter the wavelength. The lower the frequency, the longer the wavelength. Various types of sound and light can be distinguished by their wavelengths.
Different pitched sounds have frequencies ranging from high to low. The frequency of bass is about 30 Hz. In other words, it vibrates 30 times per second. This is alto. The frequency is about 1000 Hz. This is the highest pitch that can be produced on a piano, and it is about 4000 Hz.
The highest frequency of vibration human eardrums can sense is 20,000 Hz, which corresponds to a wavelength of about 2 centimeters. Sounds beyond this frequency can be heard by human ear. Sounds with frequency higher than this are called ultrasonic waves or ultrasound. You probably can't hear them because their frequency are really high.
There's also another limit. Sounds with a frequency lower than 20 Hz, which have a corresponding wavelength about 17 meters, also can't be heard by the human ear. We call sounds with such a low frequency or long wavelength infrasound. The human ear basically cannot hear an infrasound, but some animals, like elephants, giraffes, or whales, can receive and generate infrasound to communicate with each other.
Humans can hear a very broad range of sound from 20 Hz to 20,000 Hz, a range with 1,000-fold difference. In contrast, the range of light that we can sense is much narrower, as the longest wavelength that can be seen is only about 2 times that of the shortest wavelength.
Sound is classified as treble or bass according to the wavelength or frequency of the wave, whereas the color of light changes with the frequency of wave.
The human eye can sense wavelength within a range of approximately 400 nanometer to 800 nanometer, namely from red to violet. Humans can sense light with a wavelength higher than this range, such as infrared, microwave, and radio wave, or light with a wavelength lower than this range, such as UV rays, X-rays, and gamma rays.
The light that reaches the Earth from the Sun consists of a wide spectrum of electromagnetic waves, but only a small range of them is visible to humans. In spite of this, humans can still enjoy a colorful world. In 1912, a major event in maritime history occurred. The most luxurious passenger steamship ever built at the time, the Titanic, sank in the North Atlantic Ocean after crashing into an iceberg during her maiden voyage from the United Kingdom to New York City, United States.
When the crew spotted the iceberg, the officer ordered the ship to steer around the obstacle and the engine to put in reverse. Although the ship's starboard side avoided a collision with the visible part of the iceberg, her underside brushed against the massive part of it beneath the water. The underside of the Titanic brushed against the deadly edge of the iceberg. 2.5 hours later, the Titanic disappeared beneath the freezing water of the Northern Atlantic.
The exposed part of the iceberg above the surface of the sea was only a small portion of the whole iceberg. To avoid crashing into the iceberg, what is beneath the surface needs to be clearly known. However, it is very difficult for the naked eye to observe the surrounding environment with the ambient light because electromagnetic waves attenuates quickly in water. The light from the surface can hardly reach the water underneath. Since the Titanic incident, people have started to develop and employ sound reflection to look at what lies underwater. Reflection is a physical phenomenon. It refers to the process when wave passes from one medium to another and changes its direction of propagation, going back to the original medium. Sound waves can be effectively transmitted in water, so scientists make use of the echo produced when its sound is reflected to detect objects under the water.
For example, if we want to detect an underwater iceberg, sound waves are directed towards the iceberg in the sea. Then the shape of the iceberg can be known by analyzing the echo.
We can also make use of the echo to search for clusters of fish in the ocean. A fish finder emits ultrasonic waves into the sea. The fish clusters can be found by analyzing the echo received and calculating the time needed for the sound wave to travel to and back from the target.
What about light then?
When you look in a mirror, you can see yourself. It is because the reflection of light helps us to see what we can't directly see.
The light from my face shines onto the mirror and is reflected by the mirror into my eyes. As our vision can't bend like the light is therefore seen as if it is emerging from the back of the mirror, and that is how we can see ourselves in the mirror.
Compared with sound, light or electromagnetic wave can be transmitted in the air more effectively. So, by emitting radio wave and receiving the radio wave reflected by the object, the location of offshore typhoons and other flying objects, such as planes, can be detected. You may have experienced this, that the sound of bells from a bell tower or the siren of a police car sounds especially clear to you at night. You may think that you can hear distant sounds more clearly at night because it is quieter than during the day. That, however, isn't the only reason.
Have you ever taken part in a three-legged race? When two people walk together side by side, if one person walks slightly faster, then the pair can walk in a straight line and will be dragged towards the side with a slower walking speed. The key point is this: the speed of the sound in the air is affected by the temperature. The higher the temperature, the faster the speed of sound.
Now let me walk you through the principles behind. During the day, the surface of the ground is heated up by the sun. The air near the surface is also warmed and its temperature rises, while the air further up from the ground is cooler and the temperature is lower. Sound travels faster in hotter air and will refract to the sky, so it is difficult for sound to travel for a long distance. Conversely, the temperature is cooler during the night. The air near the ground also becomes cooler, while the air higher up becomes warmer than the air near the ground, so sound travels faster and further away from the ground than it does near the ground. The sound would deflect towards the ground's surface, making it easier to travel for a long distance. Thus it becomes possible to hear sounds at night that cannot easily be heard during the day.
Refraction is a physical phenomenon. When a wave passes from one medium to another, or when there is a change in the speed when a wave is traveling in a medium, there is a change in the direction of propagation. Does something similar happen for light?
Has anyone heard of a mirage? A mirage is an optical phenomenon that occurs in nature. It happens when a virtual image is formed by refraction as light propagates in the air.
The underlying principle is in fact not complicated. Cold air is denser than hot air, and light travels slower through cold air. When light passes through the boundary between cold and hot air, it will refract in the direction parallel to the boundary separating the two medium. Under the scorching sun, the sand on the ground becomes very hot. The air near the ground can become warmer than that 1 meter above it by 5 degrees or more. Light from distant object will bend away from the ground towards the sky. When seen by an observer, the light can easily be mistaken to be light from the ground. The water on the ground is actually the mirror image of the blue sky. It is just like the reflection of the scenery reflected by a lake. Why can we hear sounds from behind the wall? Same as light, sound is supposed to propagate in a straight line. How come it can climb over the wall and get around obstacles to reach our ears? It is a physical phenomenon. When a progressive wave encounters an obstacle or aperture, the path is deviated from its original straight line. This phenomenon is known as diffraction.
But light would be blocked by the wall and cast a shadow. Diffraction is a phenomenon exhibited by waves. Since light is also a kind of wave, it should also be able to diffract. However, why is it so different from sound?
The answer lies with its wavelength.
The wavelength of sounds that we can hear ranges from several centimeters to over 10 meters, and the dimension of most obstacles is usually within this range. Under such circumstances, diffraction is more prone to occurring. However, for waves of shorter wavelengths, for example, the ultrasonic waves emitted by bats, which are only several millimeters long, diffraction is not likely to happen.
Will diffraction occur in electromagnetic wave? The answer is evident. Cellular phones or radio devices can still receive radio wave around the corners and in place blocked by obstacles. It is because the wavelength of radio waves is very long, ranging from several centimeters to several meters, or even over 100 meters. Radio wave therefore can be diffracted easily. The diffraction of radio wave is the reason why we can receive calls and pick up radio bands from behind a building or around the corner.
Can light be diffracted? Let's look at this. Here is a laser beam. When it passes through a tiny hole, a pattern of bright and dark rings can be observed. How could we explain this if it isn't due to diffraction of light?
In fact, under suitable circumstances, any wave can be diffracted. Well then, what will make a suitable circumstance?